Okay, let's next talk about reference angles. Reference angles are uh, useful for finding values for sine and cosine and tangent, because it turns out that we really only need one quadrant worth of values, and we can do reference to figure out what the other ones are. So here we have a circle, and I've got some sort of angle that I'm dealing with here, theta. Um, that's good. So I've got some sort of angle in here that I'm dealing with, theta. And this circle has a radius of 1 in there. And so I know that the sine of theta is the y coordinate divided by the radius. And I'm choosing, and I know that it's constant for a given angle. I'm going to choose to make that angle 1. So then this physical distance here from the x-axis up to this point, that's the y coordinate of the point C, and that would equal the sine of theta in there. And similarly, the x coordinate here is going to be the cosine of theta. The cosine is going to just be the x coordinate because the radius that I'm dealing with is 1 in there, in that little right triangle that I'm working with here. The sine would be the x coordinate or the y coordinate, the cosine is the x coordinate. We call this the unit circle. A lot of times we work in the unit circle um, because it's just convenient to work with, where this physical distance is the sine, this physical vertical distance here from your point down to the x-axis is the sine in there. But if I'm looking at this circle, I've kind of drawn them out here for us, but there are 4 other points. Well, there's a total of 4 points with the exact same y coordinate in size. Some of them are different in sign, but F down here has the exact same y coordinate. This distance, this vertical distance is the exact same as what we have in the first quadrant. So this would be the same exact sine value, but it's going to be a negative value. So if I had my angle to start at the origin and go all the way around to there, I would say that that sine value is the exact same as the sine of theta, but it's just going to be negative instead of positive because it's the same vertical height. It's just negative because it's in the second quadrant. Or if I measured my angle going in the negative direction, I'd have that same angle, but it's going to be a negative value in there. There's other point over here, point E. Our vertical distance down to the x-axis is the same as it is at point C. And so I know that the sine of the angle starting at 0 and going around to that point would be the same as the sine of whatever theta that I have in here. Let's throw some numbers in there to kind of make us make things make sense a little bit more in there. Let's kind of clear out some of this thing in here. So that if this angle is, say, 20 degrees here, if that's a 20-degree angle, I know that the sine of 20 degrees is going to be the same as the sine of 160 degrees, right? That this would be from that if that's a 20-degree angle in there, this would be a 20-degree angle in there as well. And so the sine of 160 is the same as the sine of 20. And if I go a little bit farther, I know that the sine of 20 degrees is going to be, well, if I change the sign of that, I'll get the same as the sine of 200 degrees, right? Because if I go from the positive x-axis all the way around into the third quadrant here, I'm going to end up with a same y value here, but it's going to be negative because it's below the x-axis in there. And so what we refer to is that all of these angles have a 20-degree reference angle. That if you can relate it back to the first quadrant, a 20-degree angle. All of these 4 angles, there's 4 of them all together, maybe even more if you want to look at it. So you've got minus the sine of 20 degrees is the same as the sine of, let's see, that's going to be 360, take away 20 would be 340 degrees. The sine of 340 is the sine is the same sign, same size, same size as the sine of 20, but opposite in size. And so what we have is a reference angle for those. And every angle that you have that's bigger than 90 degrees has a reference angle that's between 0 and 90 degrees. And the way that you find it is you always go to the x-axis. So from wherever you end up, you want to look at how far do you have to go to either get to the x-axis going forward or going backwards. If you've gone past that 180 degrees, what's the shortest distance to the x-axis from that point? And that will give you your reference angle in there. Let me kind of clean this up. I hope that's kind of making sense. I'm going to get rid of everything that I've got here. Erase everything and change my angle a little bit there. All right, give me my pointer back. Let's change this to a different angle in here. So now I've got an angle of maybe I don't know what angle that is. Maybe say 75 degrees. Let's suppose that that is, I'm not sure if that's exactly 75 degrees, but let's say that that's a 75-degree angle in here. Well, other angles with that same sine would be 105, right? If I go from the origin all the way up to this one, 105 degrees, that I know that the sine of 105 degrees is going to be the same as the sine of 75 degrees. Those two values, that these 2 points C and E, have the exact same y coordinate. They have the exact same y coordinate. Their x coordinates are also the same in terms of size, but not sign. I know that the cosine of 75 degrees is going to equal minus the negative cosine of 105. They're going to have the same value, 105 degrees in there, that they're going to have the same value, but the cosine here would be negative in that instance, because I'm more than 90 degrees. My angle is popped into the second quadrant, so that the cosine is going to be negative in there. And actually, that's something to note, that that in the unit circle, the cosine or the sine is the y value, and in the first quadrant, all are positive. In the second quadrant, the sine is going to be positive. Your y coordinate is still going to be positive, but your cosine is going to be negative to end up here in the second quadrant. Your x coordinate is going to have a negative value. Your y coordinate is going to be a positive value. So the sine will be positive. Cosine and then tangent. Tangent is the y coordinate divided by the x coordinate. So it's going to be a positive number divided by a negative number. It's going to be negative in that one. In the third quadrant, the tangent is positive, but sine and cosine are negative. If I end up down here in the fourth quadrant, both the x coordinate and the y coordinate here are going to be negative values. But if you divide a negative by a negative, you end up with a positive. So the tangent would end up positive in there. Tangent was the y coordinate divided by the x coordinate, but those two are both negative numbers. So a negative divided by a negative gives you a positive. And then down here in the fourth quadrant, the cosine is positive in there as well. So cosine is your x coordinate. If you're down here, if you've got an angle all the way down here in the fourth quadrant, the cosine, the x coordinate of that angle, is going to be positive. The y-coordinate would be negative, sine is going to be negative, cosine would be positive, and then tangent as a result is negative because it's going to be the negative sine value, negative y-coordinate divided by the positive x-coordinate, so it would be negative. So they're all positive in this quadrant. Sine is positive in the second quadrant. In the third quadrant, tangent is positive, and in the fourth quadrant, cosine is positive, and the other two are negative. I've heard the mnemonic, all students take calculus, so they're all positive here. The students is positive in that one. T for take, tangent is positive in that one, and C for calculus or for cosine. So if you go counterclockwise, numbering in the quadrants, all students take calculus. You get how they go. That they're all positive here. Sine is positive in the second quadrant. Tangent and cosine are negative. Tangent is positive in the third quadrant. Sine and cosine are negative. And the cosine value that you look at for an angle that ends here in the fourth quadrant would be positive, where sine and cosine are negative. But the reference angle is the angle back to the x-axis. So if you have a reference angle of um, it's really nice to look at there. And what's even nicer is looking at the special angles. That if our angle, if I take a 30-degree angle, that if you take a 30-degree angle, let me move this back down to 30 degrees or something approximately 30 degrees here. Let's see, the y-coordinate would be a half at 30 degrees. So that's a 30-degree angle in there. That this angle of 30 degrees, give me back my pen, that this angle of 30 degrees, that the y-coordinate here is going to be 1/2, 30 degrees or pi over 6. Our other angle that we had when we went all the way around this one, when I had a pi over 6 reference angle, this angle was 5 pi over 6. And the y-coordinate here is also a half. The x-coordinate would be minus √3 over 2. The x-coordinate is positive √3 over 2 in that case. At 7 pi over 6, sine is also equal to a half, but it's going to be negative because it's in the third quadrant. So the y-coordinate here is 1/2. And then down here at 11 pi over 6, our sine is negative. The y-coordinate is negative 1/2. So in all of these pi over 6 reference angles, the denominator is pi over 6. The sine is always a half. So if I've seen something 5 pi over 6, 7 pi over 6, 11 pi over 6, as long as we've got a reduced fraction and we got a 6 on the bottom, I know that the value of the sine is going to be a half, and I just need to decide whether it's positive or negative based on what quadrant I end up in. Same thing happens with a pi over 3 with a 60-degree angle. If I move this angle up here to 60 degrees, if that's the y-coordinate is √3 over 2, the y-coordinate would be square root 3 over 2 with a 60-degree reference angle, a pi over 3, a reference angle of pi over 3, and an angle of 2 pi over 3. That y-coordinate is still √3 over 2. And then I just need to worry about, is it in the first quadrant, the second quadrant? In both of those, the sign is positive. In the third and the fourth quadrant, it's negative. So if you've got a pi over 3 reference angle, if it's something over 3, pi over 3, 2 pi over 3, not 3 pi over 3. 3 pi over 3 reduces to just pi. That's 180 degrees. But 4 pi over 3, or 5 pi over 3, will also give you values where the y-coordinate is √3/2, but they will both be negative because they're in the second or the third and fourth quadrants respectively in there. So reference angle, when you're looking a um, at a circle, your reference angle is always the angle back to the x-axis. Let me clear all drawings there. So when you're looking inside a unit circle, uh, if we've got our unit circle in here, or any circle at all, if you've got some sort of angle that you're working with, if I got an angle that ends over here, my reference angle would be the angle going back to the x-axis. That would be the acute angle in there. That reference angle is going to have the same x-coordinate and the same y-coordinate as if that equivalent angle was in the first quadrant. It's going to have the same x-coordinate and the same y-coordinate. If you've got something that ends here in the second quadrant, then my reference angle would be the angle in here from that line on down to the x-axis. The y-coordinates would be the same, referring back to that same size angle, but they're going to be in the different quadrants. All right, so reference angle is a very useful tool. You can find the values of sine and cosine by looking at figuring out what the reference angle is in there. And then you have to worry about whether it should be a positive number or a negative number. Sine, cosine, and tangent. That all works for them.